Hi, Frazier Nyasulu again. Today, when I talk about decomposition reactions, and in particular potassium chlorate, how does that decompose? Once we profile and understand how that decomposes, we'll then take that knowledge and use it for the analysis of a mixture consisting of potassium chloride and potassium chlorate. Gotta know your polyatomic ions. ClO3 is chlorate. Get the slide version and then pick up pointer options. All right, so let's go. Potassium chlorate. Decomposition. How do you get it to decompose? Well, in this case, we get it to decompose by heating strongly. So potassium chlorate is reasonably stable under room temperature conditions. But if you heat it, that's what this arrow means. Not this arrow, but this thing above the arrow just means heating. If you heat it, and in our case heating with a Bunsen burner, you can get it to decompose. And for now, we'll speculate that the products are potassium chloride and oxygen. This is a solid, this is a gas, so if this reaction occurs, we can anticipate that the oxygen just joins the air. So, how about if we say, let's confirm that the products are as indicated. That is potassium chlorate, KCl and oxygen. And again, we take that knowledge and use it for the analyzing of the mixture. So, when you do this reaction, it'll be clear to you that a gas is produced. Now, the question is, what is the gas? So we kind of use our knowledge, little chemical knowledge, to speculate what that gas could be. One could say, hey, looking at the reactant product reactions, it could be K gas, potassium gas. Like, really? Well, probably not. But let's write it in there. Potassium gas, that would be the potassium atom, so you'd go from potassium ion to the atoms like, It could be chlorine gas, Cl2, not Cl but Cl2. It could be Cl2O, and it could be oxygen. Maybe one could dream up other possibilities, but these sound reasonable, although one or two of these are kind of far-fetched. If we speculate that those are the products, then maybe the gaseous product, can we identify what the gas is? And that's where our burning splint smoldering splint comes in. If we decompose a gas and suppose that the gas is produced and we test with a glowing splint and it burns very strongly, ignites in this case and gives us a fervent flame, then that would indicate that the gas is oxygen, because oxygen supports combustion. And so in our case, that's what we're really going to do. We're not going to test for all these others. We're going to just test for oxygen. We kind of know. So it's confirming that the gas produces oxygen. How about that other part? What's the other part? The other part is an ionic compound. We start with ionic compound, the potassium chlorate on the other side. And so there is potassium, and there is babies that arise from ClO3. This is the starting compound. So then it's potassium and the chlorate ion. So it's like, okay, there's oxygen coming out. This is the only location for oxygen. So some of that goes out. So maybe I'll speculate that the counter ion to potassium is this one, going from 3 to 2, That one or the chloride ion? And then in our test, we'll actually just test for the chloride, kind of really confirming it is chloride. Well, what's the test then? The test says if you can take some of the residue after you heat and it decomposes, take some of the residue, dissolve it in water. If the anion to the potassium is chloride, then you get what is a precipitation reaction. That is Ag plus. If you add Ag aqueous and to this solution, then you form AgCl solid. That's a white precipitate. So if we do this in a test tube, we take some of our residue, dissolve it in a little water, and then put drops, 3, 4, 5 drops of what is a solution containing Ag plus. It'll be silver nitrate in this case. Then as we add that, we'll actually see a white precipitate form. If that is done, then that confirms, in our case, that the product is KCl. So we'll have confirmed the gas is oxygen and the other product is KCl. Great. Now let's examine potassium chloride carefully. Their mass is in the periodic table, you know that, atomic mass units. And so we can get, okay, there's one of these, one of that, and 3 of those. And so we can say in the AMU then the total for potassium chloride is 122.55 AMU. What can we do with that? Hey, if you look at me, one person, one Frazier Nyasulu, one Frazier has 2 eyes, 1 nose, 10 toes. So we can begin to write relationships between the components that are in KCl. We write equivalent relationships. So you can say one person is equivalent to 10 toes. One person is equivalent to 2 eyes. You can't say one person is equal to, it's equivalent relationships. So here we go. So 122.55 AMU KClO3 is equivalent to 35.45 AMU of chlorine, and similar to the others. But as you know from looking at these definition of moles, we can actually convert from AU into moles. So we can say, in the manner of speaking, 122.55 grams of KCl contains 35.45 grams of Cl. Contains. But we'll write this as an equivalent relationships. Similarly for the potassium and for the oxygen. So we have 3 equivalent relationships. 3 equivalent relationships. They're right here. 122 is equal to that one. 122 is equal to this one. 122 is equal to that one. Here. And you write it as grams KClO3 is equivalent to 48.00 grams oxygen. That's how you write it. And then once you've done that, building on last week's lab, we can do dimensional analysis. Last week's lab or two labs ago, whatever. Dimensional analysis. So we can say calculate the mass of that needed to produce 332 grams of, assume it's oxygen here. Here is what you're given. You take the relationships, the equivalent relationships that we just talked about, and for cancellation you need 122.55 grams of that over 48 grams of oxygen, and then of course the oxygen cancel out, grams of oxygen, and you do the arithmetic and you get grams of KClO3. So if we have a mixture of KClO3 and KCl and heat it and decompose all the KClO3, then what? Then the mass of whatever we start with will go down because the oxygen is leaving. So from a difference in mass, we can find the grams of oxygen. From the grams of the oxygen, we can go back and find the grams of KClO3 that begat or produced the oxygen. And then from that we can find the percent mixture. There it is. Aha. That to that to that, and then we're done. So here is the crucibles that you're going to work with. And the little price of these, so be careful. I think $10, $12 for the cover. Similarly for the lower component. But anyway, this is how you transport these things, especially when they're hot. The hand there with wire gauze just provides additional insurance in case it slips or anything slips, so you can catch it before it breaks. That's the heating system. You usually wanna the cover, just let it so that it can let out little of the oxygen that's being produced. You don't want it sealed because then that will pressurize, and pressurized systems not good. Yes. So that's the setup. Hot is hot. So handle the crucibles that way by using the tongs. That's the heating system there. Lead slightly offset. So that's what we're doing in lab today. Again, briefly, first part, analysis of decomposition of the products. Add some stuff to the test tube. Cover it with parafilm. When you cover it with parafilm, you want to cut a little hole. We don't want the system to pressurize, so when you cover it with parafilm, you cut a little hole in the middle so some of the gas escapes, but we keep some of the oxygen in there so we can test and confirm that it's oxygen. And this reaction we'll do in a test tube. And then we'll take the residue and test for chloride by dissolving a little of it in another test tube and adding a solution of silver nitrate, and then seeing if a precipitate is formed or not. There it is, yeah. And then we're ready for the heating. This is a strong heating. So essentially, after we get the crucible ready, cleaned and whatever it is, we'll add about 1 gram of the mixture, okay, and record the mass. So we'll record the mass of the crucible alone, and lead alone, and then from there add 1 gram of the mixture. Heat the mixture with the Bunsen burner. You want to heat strongly. So you should be able, if you're heating strongly, to see the bottom of the crucible glow nice and red. You start slowly, and then you can increase the heating intensity. It's got nice and red color when you get to heat maximum rate. And then we'll let the system cool. Let it cool. How do I know when it's cooled? How do I know? Just watch your time. Let's give it 7 to 10 minutes after stopping the heating. It was sufficiently cold. So take a look. We'll watch somewhere in the lab. Okay, it's 7:15, and it's not 7:15. I don't know. Whatever time. And so you can go on and add 10 minutes, whatever it is, and then wait. But the question is, how do I know the reaction is complete? That is, the decomposition reaction is complete. Well, how do I know I've stopped growing? I need a few more inches on me. Yeah. Well, I measure myself today, measure myself next year, measure myself 5 years down the, like, ooh, the number is the same. So do the same here. Essentially, we'll heat and weigh until we get a constant mass, or changes that are kind of errors within 20 milligrams are acceptable. And so that's how we'll know we're done. And then we're ready to grow. Nothing toxic here. We produce potassium chloride, a benign product. So wash it down the sink. This just describes what I talked about earlier. Heat, cool, weigh, preheat, cool, weigh until you're seeing a difference of less than 10 milligrams. Safety. I'm responsible for your safety. Ha! You are responsible for your safety. I'm responsible for your safety. So, we're going to be safe out there today, in your lab this week. What is hot? Crucibles are hot, and you don't want to touch it while it's still hot. So, err on the lot of time to cool side. Before starting, make sure the crucible doesn't have any cracks. If it has any cracks, exchange it from the stockroom. In part A, where you're using a test tube, sort of when you heat, move the flame in and out so that we don't create I've seen test tube kind of break if continuous and strong heating is applied. So in and out, and the slit on the parafilm just to allow excess oxygen or whatever it is to get out. We don't want the system to build any pressure. And then you can wash down the products with excess water. That's your lab today. Do good work, have fun, learn. See you in lab.